The MAF sensor, the engine's lungs and brain. In the intricate ballet of the internal combustion engine, where fuel and fire dance in a precise rhythm, one component plays the critical role of choreographer. It is the silent, unseen sentinel that measures the very breath of the engine. This is the story of a device that transformed automotive performance, efficiency, and emissions, the Mass Airflow Sensor, or MAF. For decades, engines were mechanical beasts. Airflow was estimated, not measured. Carburetors, brilliant in their mechanical simplicity, relied on pressure differences and vacuum, but they were imprecise, wasteful, and dirty. The quest for cleaner air and the 1970s oil crisis demanded a revolution. The engine needed to know, not guess. Before true mass airflow sensors, engines used a clever workaround: the speed density system. The speed density system was the first step towards intelligence. It didn't measure air directly. Instead, it used a manifold absolute pressure sensor, the MAP sensor, to read air pressure inside the intake manifold. The engine control unit would then cross-reference this pressure with the engine's RPM and air temperature to calculate an air mass. It was effective, but like any calculation based on multiple variables, it could be thrown off by changes in camshaft timing, exhaust back pressure, or engine wear. The system was indirect. The engine's brain was working with estimates, not facts. For precise fuel metering, especially under rapidly changing load, a direct measurement was needed. The first production car to use a true airflow sensor was the 1975 BMW 2002 T, but it wasn't a mass sensor, it was a volume sensor. Developed by Bosch, the vane-type airflow meter, or VAF, was a mechanical marvel. A spring-loaded flap was positioned in the intake air path. As air flowed, it pushed the flap open. The angle of the flap was directly proportional to the volume of air entering the engine. A potentiometer attached to the flap would send a variable voltage signal to the control unit. It was a major leap forward, used famously in early fuel-injected cars like the Porsche 911, Volkswagen GTI, and BMW 3 Series, but it had critical flaws. The mechanical flap created intake restriction, robbing the engine of power. It was slow to respond to rapid throttle changes, and it could only measure air volume, not its mass. Since cold, dense air has more oxygen than warm, thin air, the system still required corrections from other sensors to get the fuel mixture perfect. The breakthrough came from applying a century-old principle, the hot wire anemometer, used to measure fluid velocity. In the early 1980s, Bosch and Hitachi led the charge in adapting this for the automobile. The result was the hot wire mass airflow sensor. Its principle was elegant and brilliant. A thin, electrically heated wire, typically platinum, is placed in the intake stream. The engine control unit keeps this wire at a constant temperature differential above the incoming air temperature, say 100 degrees centigrade or 200 degrees centigrade hotter. This is where the genius lies. As air flows over the wire, it cools it down. The ECU instantly compensates by sending more current to the wire to maintain its target temperature. The amount of current required is directly proportional to the mass of the air flowing past. More dense air pulls more heat, requiring more current. It's a direct, real-time measurement of air mass. This was a paradigm shift. No moving parts, minimal intake restriction, and crucially, it measured mass, not volume. This gave the ECU the most accurate data possible to calculate the perfect fuel injection pulse width. The first widespread use was in the mid-1980s on cars like the Bosch Metronic systems. The hot wire was brilliant but delicate. The exposed wire was susceptible to contamination from oil and dirt, which would insulate it and cause inaccurate readings. The solution was the hot film MAF sensor. Instead of a thin wire, a thin layer of platinum is deposited onto a durable ceramic or silicon substrate. This film is far more robust and resistant to contamination. It operates on the exact same principle, but is cheaper to produce and more reliable for daily use. Nearly all modern hot wire MAF sensors are technically hot film sensors. Today, the MAF sensor is rarely alone. It is part of a sensor suite. Many modern systems combine a MAF sensor with a built-in intake air temperature sensor. Some even integrate a barometric pressure sensor. This provides the ECU with a complete, real-time picture of the air charge entering the cylinders. However, the quest for perfection continues. MAF sensors can still be fooled by turbulent air, pulsations from the engine's intake strokes, and most commonly, contamination. The modern trend is sensor fusion. Many high-performance engines now use a hybrid system that combines a MAF and a MAP sensor. The MAF provides precision during steady-state and light-load conditions, while the MAP sensor's rapid response is used for transient conditions like sudden acceleration. The ECU uses the strengths of both to achieve a level of control that neither could manage alone. As the world shifts towards electrification, the role of the MAF sensor in its traditional form is diminishing. The electric motor has no need to measure air. However, its legacy of precise measurement lives on. In hydrogen fuel cell vehicles, mass flow sensors are critical for precisely metering hydrogen gas. In advanced battery thermal management systems, the principles of flow measurement are used to monitor and control coolant flow. The knowledge gained from perfecting the MAF sensor is now being applied to manage the flows of new energies. From a simple, restrictive flap to an invisible, heated film of platinum, the mass airflow sensor's evolution mirrors the automotive industry's own journey from mechanical brute force to electronic intelligence. It is an unsung hero, a device that gave the engine not just lungs, but a conscious understanding of every breath it takes. It made our cars more powerful, more efficient, and infinitely cleaner, proving that sometimes the most profound revolutions are measured not in horsepower, but in milligrams per second. We have traced the MAF sensor's evolution from a mechanical flap to an electronic sentinel, but its full story is written in the language of failure modes, diagnostic codes, and the constant battle for perfection in an imperfect, dirty world. For a device that must remain pristine to function, the MAF sensor lives in a hostile environment. The very air it measures carries its enemies. Oil and dirt, the primary killer. A poorly maintained air filter or an over-oiled aftermarket performance filter can coat the hot film in an insulating layer. This layer acts like a blanket, preventing the element from cooling properly. The ECU, seeing less cooling, reads this as less air and leans out the fuel mixture, causing hesitation and misfires. Silicon poisoning, a more insidious threat. From silicon sealants or certain types of gasket materials, vaporized silicone can bake onto the hot element, forming a glass-like permanent insulation that cannot be cleaned. Backfire damage, a sudden explosion in the intake manifold. A backfire can send a shockwave that physically snaps the delicate hot wire or film. Electrical failures. The sensor's internal circuitry can fail, providing no signal, a constant signal, or a signal that is out of range. A contaminated MAF is the great deceiver. The car feels sluggish, it might stall, the check engine light comes on. But because it's not a hard failure, many people misdiagnose it as a bad fuel pump or ignition coils. The data from a bad MAF is plausible but wrong, which makes it one of the trickiest problems to pin down. Diagnosing a MAF sensor is a lesson in digital forensics. The modern technician doesn't just replace parts, they interpret a stream of data. The key parameters are MAF voltage and airflow in grams per second. At idle, a typical engine might read around 1 volt and 37 grams second. At wide-open throttle, this can surge to 4.5 plus volts and over 200 grams second. The diagnostic ritual is precise. 1. Scan for codes. Codes like P0100 MAF circuit malfunction or P0101 MAF performance are the starting point. 2. Live data analysis. The technician watches the graph. Is it smooth? Does it respond instantly to throttle blips? A lazy or noisy signal is a dead giveaway. 3. The unplug test, a classic technique. With the engine running, unplug the MAF sensor. The ECU will default to a speed density calculation using the MAP sensor. If the engine runs better with the MAF unplugged, the MAF is almost certainly the culprit. In the world of high-performance engine tuning, a great debate rages: MAF-based systems versus speed density or K-manifold systems. This is more than a technical choice, it's a philosophical one. The MAF argument: precision. Proponents argue the MAF provides the most accurate measurement of actual air entering the engine, leading to perfect fueling under all conditions, especially steady-state cruise. The speed density argument: resilience. Enthusiasts, particularly in motorsports or for heavily modified engines, often remove the MAF. They argue that a well-calibrated MAP sensor-based system is more robust, has no intake restriction, and isn't fooled by wild camshafts or forced induction setups that create turbulent, nonlinear airflow that can confuse a MAF sensor. It's about control versus adaptation. A MAF system is brilliant for a stock, predictable engine, but when you're pushing boundaries, the MAP-based speed density system gives me, the tuner, absolute control. I'm telling the ECU, at this RPM and this manifold pressure, inject this much fuel. It's a pre-calculated map of perfection. The MAF is always reacting, speed density is predicting. The next evolutionary step is already happening at a scale invisible to the human eye. The latest generation of airflow sensors are based on MEMS technology. These are microscopic mechanical elements etched onto a silicon chip, just like a computer processor. These sensors are smaller, cheaper, more robust, and fast-responding than their hot-wire ancestors. They can be integrated directly into the intake tubing, eliminating the traditional sampling tube altogether and providing an even less restrictive path for air. The mass airflow sensor is a testament to the idea that the most significant progress is often made in the realm of measurement. You cannot control what you cannot measure. This unassuming component, often no larger than a matchbox, has been an invisible hand guiding one of the greatest environmental success stories of our time, the cleaning of the automobile. By giving the engine's computer a perfect understanding of its own breath, it enabled a level of control that slashed emissions and doubled efficiency. It is a bridge between the analog past and the digital future, a humble component that taught a mechanical beast to think, to adapt, and ultimately to breathe cleanly. We have seen the MAF sensor as a governor, a victim of contamination, and a tool for tuners. But its story is also one of control, biology, and a silent, ongoing negotiation between the driver, the machine, and the corporation that built it. As MAF sensors and the ECUs they feed have grown more complex, they have become black boxes. Their internal logic and calibration are fiercely guarded corporate secrets. This has ignited a pivotal modern conflict: the right to repair. The MAF sensor is a perfect microcosm of this battle. It's a simple physical component, but its language, the data stream, is proprietary. Manufacturers argue this protects their intellectual property and ensures repairs are done correctly. But in practice, it can lock out independent mechanics and owners, creating a monopoly on service. It transforms the car from a piece of property you own into a service you are merely allowed to operate. Fault codes from a failing MAF can trigger limp mode, a state where the manufacturer's software deliberately cripples the car's performance to prevent damage. This protective measure is also a powerful form of control, forcing the owner to seek an authorized solution. To truly appreciate the MAF sensor, we can view it not as an electronic component, but as a sensory organ. It is the engine's proprioceptor, the internal sense that allows an organism to understand its own state and interaction with its environment. It's a beautiful example of convergent evolution between biology and engineering. The human body has the carotid sinus, which measures blood pressure and oxygen levels. The MAF sensor does the same for the engine. Both are delicate, vital sensors that provide real-time feedback to a central processing unit, the brain or the ECU, which then makes instantaneous, life-sustaining adjustments. A failure in either system leads to a catastrophic loss of homeostasis. This metaphor extends further. Just as the body can develop atherosclerosis, plaques that narrow arteries and distort blood flow, the MAF sensor can suffer from contamination that insulates it and distorts its reading. In both cases, the system is fooled into a state of malfunction. A failing MAF sensor does more than cause poor performance. It shatters the driver's trust in the vehicle. The car, an extension of the self, becomes unpredictable. This subtle, intermittent failure creates a state of hypervigilance and anxiety in the driver. The driver enters a psychological feedback loop. Is it the fuel? Is it the spark plugs? Is it me? The machine, which should be a source of agency and freedom, becomes a source of doubt. Restoring the MAF sensor is not just a mechanical fix. It is a restoration of a broken relationship. A return to predictability and control. In a fascinating counter-narrative, many modern diesel engines have abandoned the MAF sensor altogether. They are the ultimate speed-density machines. Because diesel engines are fuel-throttled, they control power by metering fuel, not by restricting air, and because they always operate with a large excess of air, knowing the precise air mass is less critical than in a gasoline engine. The ECU can perfectly manage combustion using the MAP sensor, crankshaft position sensor, and sophisticated models of the turbocharger's behavior. This represents a different path to efficiency, one that sidesteps the fragility of the MAF. As we stand on the brink of autonomous transportation, the humble MAF sensor's legacy is secure. It was one of the first components to teach the automotive industry a critical lesson. For a machine to be truly intelligent, it must first be exquisitely aware. The MAF sensor was the vanguard. It proved that reliable, real-world data was the key to unlocking efficiency, power, and cleanliness. The LiDAR, radar, and cameras on a self-driving car are the spiritual successors to the MAF, a new generation of sensory organs for a new kind of machine consciousness. The mass airflow sensor's story is a quiet epic. It is a tale of a technology that began by measuring a simple physical property, the cooling of a hot wire, and ended up reshaping our environmental landscape, redefining the relationship between humans and their machines, and laying the foundational philosophy for the robots that will someday share our roads. It is the whisper in the machine's ear, telling it who it is and how to live in the world. And in doing so, it taught us that the path to a smarter future is paved not just with faster processors, but with better, more honest senses.